Welcome to this third lecture in our programming language series on functional programming with Haskell. To start with, I'll quickly give you an overview of the difference between functional and imperative programming, and then we'll start looking at the specific features of Haskell, in particular pattern matching, referential transparency, lazy evaluation, recursion, and finally higher order and create functions. There are various resources that I'll be using in this course. One of the main ones which I referred to you is the classic ACM Computing Surveys article by Paul Hudak on conception, evolution, and application of functional programming languages. You'll find a link to this paper on the course website and also in the PDF of the slides. First of all, a little bit of history. Before the very first computer was even designed, Alonzo Church introduced the lambda calculus in the early 1930s. This is a formal model of computation, just like Turing machines are a formal model of computation, but the lambda calculus is more language-oriented rather than computer-oriented. The lambda calculus can be seen as the foundation of several different kinds of programming languages, has a strong affinity to functional languages. McCarthy introduced Lisp, which was a language for symbolic computation using lists, in 1960. We saw that briefly in the first lecture in this series, and it also has a strong affinity to the lambda calculus. Iverson's APL is a language which has some similarity to Mathematica, which followed much later. It also has a strong functional flavor with a very compact notation. Landon's paper on ISWIM, or If You See What I Mean, was a paper designed for essentially a functional language. And if you read that classic paper, you will see many of the concepts we see in Haskell introduced there. ML, as we've also heard before, was introduced at the University of Edinburgh in the 1970s. It came out of a research project on theorem proving, and it was originally intended as a so-called meta-language, that's what ML stands for, to support theorem proving, but it ended up being a powerful functional programming language in its own right. Around the same time, in the late 70s, several researchers honed in on the idea of lazy evaluation. So ML is strict evaluation, as we'll see, like most programming languages. When you have an expression that is passed to a function, that expression is evaluated before the body of the function will precede its execution. With lazy evaluation, you wait to evaluate any arguments until they're actually needed. This turns out to be a very, very powerful concept, and we'll see a little bit of that later today. During the late 70s and early 80s, there was a lot of research into functional programming languages, and many, many different languages were developed. At a certain point, researchers decided that in order to make some progress, they had to join forces together, and Haskell was a project to define a common language which would on one hand integrate many of the standard innovations, and secondly serve as a basis for further research. We'll be using Haskell in the lecture today. In this slide we see the fundamental difference between the imperative and functional programming styles. On the left we'll see a factorial function. It's computed in a classical way with the help of two variables n and a, and a loop which cycles around, accumulates the value of factorial in the variable a while reducing n until it reaches the value 0. In the functional style, we write something which resembles more a mathematical notation. So factorial of n is 1 if n is 0, otherwise it's n times factorial of n minus 1. This is very nice and elegant. However, notice in particular what's interesting in the functional style, we do not modify any variables. In fact, n is simply a value that's passed in. It's used in a multiplication and a subtraction, but the variable n is not modified itself. So in a pure functional language, we have no side effects, no modification of variables. Languages like ML are not purely functional, so they actually do allow us to modify variables, but languages like Haskell do not. So programs are constructed entirely by composing expressions. So if the imperative programming style or paradigm can be described as programs existing of algorithms manipulating data, then the functional programming style can be described as functions composed with other functions, or alternatively that programs are transformations from input data to output data. In pure functional languages, all programs and procedures are functions. We have no variables or assignments or any side effects to variables at all, only input parameters. We don't have loops, although we can simulate them, but essentially we use recursion and recursive functions. Very important, the value returned by a function depends only on the values of its parameters. It doesn't depend, for example, on any global variables, on any kind of environment. And as a consequence, we have the very nice property that's called referential transparency. We'll hear about this later, which ensures that every time we evaluate a function, we'll get the same result. Finally, functions are first-class values. So this means that a function is a value and can be passed as a parameter to another function. This gives us something very powerful, which is known as higher-order functions. What's Haskell? So we've seen that Haskell is a result of a collaboration between many developers of functional programming languages. Let's focus here on the parts in red. So Haskell is a general purpose language, which means it's a pragmatic language for building real applications. It's purely functional, so there are no side effects. It supports higher order functions, so functions that take other functions as parameters. It has non-strict semantics. So what this means, a function is strict if its arguments have to be evaluated before the body of the function can be executed. In a non-strict language, you can have a complex expression passed into a function and it's only evaluated if it's actually needed. That is, it's lazily evaluated. This is very powerful, as we'll see later. Haskell supports static polymorphic typing. We'll see more about that next week. It suffices to say that static typing means that before you run the program, it can be fully type checked. So on the basis of Haskell code, we can check that it's type consistent. Polymorphic means the opposite of monomorphic. Instead of everything having a single type, functions can have multiple types. This we already know from object-oriented programming, where, for example, a method may take as an argument not an instance of a single class, but instances of multiple classes and subclasses. We have a similar kind of feature in Haskell, but it's more closely related to generics from that we also know in languages like Java and C++. Again, we'll see more about this next week. Haskell also supports provides support for user-defined algebraic data types. This is similar to, but still different from, the feature in object-oriented languages where we can define abstract data types as classes. As we'll see, the way that works in Haskell, it gives you a similar expressive power, but it has a very different, works in a very different way from object-oriented languages. In particular, there's no such thing as subclasses in Haskell. Functions can be defined in a variety of ways, including using pattern matching, as we'll see in a few moments. And Haskell also supports list comprehensions, which are very elegant ways of defining a set of values. Here's hello world in Haskell. Pretty simple. Here we've defined a function called hello, which takes a single parameter, which is null, and as its body it will print the string hello world. Let's take a quick look at how we can run Haskell programs from the terminal. Here we are in the directory containing all of the examples for these Haskell lectures. We start the Glasgow Haskell interpreter by running GHCI. There are instructions on how to install it. And here we're given an interactive shell where we can type expressions like 3 plus 4, which are evaluated directly. We can also define a function. So for example, we can define hello to be equal to print hello. And now we can evaluate hello by passing it an empty argument. Of course, a much simpler program, a hello world program, would be simply to evaluate the string hello world. So this might be thought of as the simplest and most elegant program for hello world in any language. If you want to load any of the programs, you simply run load, the name of the file. It gets loaded and executed, and now we can run, for example, our factorial function, which is defined in the intro example file. So let's dive into the concrete features of the Haskell language, starting with pattern matching. There are actually multiple ways of specifying functions in Haskell. Two of them are based on case-based definitions. So the first is using patterns. So here we see factorial prime, our second definition of factorial, has two definitions, and the definitions each make use of a pattern. So if the call to factorial prime matches the pattern factorial 0, then it evaluates to 1. Otherwise, it might match factorial prime n, where n is any other number, and then it will result in n times factorial prime of n minus 1. The pattern-based style is quite elegant and documents in a very explicit way what the various cases are. Another style that's also supported by Haskell, which I don't like as much, but is perhaps a little bit more flexible and powerful, is using guards. So here factorial double prime n has multiple definitions separated by OR bars and equal signs. In between the OR bar and the equal sign is a Boolean expression which must be evaluate to true. So if n is 0, then we return 1, and if n is greater than 1, then we return n times factorial double prime of n minus 1. Notice that if none of the guards are met, then the result is undefined. Lists are basic data structures in Haskell, as they are in most programming languages. A list is formally, as was the case in the Lisp programming language, it's a pair of elements, and the pair consists of an element and a list. To break the recursion, the empty list is written as square brackets with nothing in between, and the colon operator constructs a new list from a head and a tail, where the head is an element and the tail is a list of elements of the same type. In order to write lists in a more convenient way, so not to have to construct lists with colon all the time, you can also use the square bracket notation and commas to list the elements of the list. So square brackets 1, 2, 3 is actually just syntactic sugar for 1, 2, 3, empty list. Of course, the first version corresponds much more to what we're used to as syntax for a list. Another very convenient notion is the double dot notation. So square brackets 1 dot dot n stands for the list from 1 up to n. Now, in order to use any complex data structure in Haskell, you have to tear it apart. So you have to deconstruct it in order to access whatever it contains. This is a little bit opposite from the way things are done in object-oriented languages, where the data abstractions themselves protect what's inside them and offer instead methods which access the internal data. So here, to do something with a list, you need to take it apart using the constructor as a pattern. So what's the constructor for the list? Well, the constructors are only two. One constructor is the empty list, and the other is head colon tail of list. So to take it apart, you use those same constructors as patterns. So here, if we want the head of a list, we write a function that takes as a pattern x colon anything, and that allows us to access the head of the list. So the head of a list which has been constructed with x colon something is simply x. Now we can define other functions, like, for example, length. So the length of a list, again, in order to compute the length of the list, we need to deconstruct it. So the patterns, the two patterns that we have for constructing lists are empty list and colon. So there should be similarly two definitions for the length function. So the length of an empty list is 0, and the length of a non-empty list is 1 plus the length of its tail. Notice that we're using underscore as a wildcard. So in the head function, we don't care what the tail is, whereas in the length function, we don't care what the head is. So we simply don't give it a name, and we use underscore. Now, since there are two constructors for list, you would expect any function that manipulates a list to have two patterns to match. Head is an exception because the head of an empty list isn't defined. So we simply leave out that pattern. So if head is called on an empty list, that should give us an error. Suppose we want to compute the product of a list of numbers. Well, the product of the empty list is going to be 1. The product of a non-empty list is going to be the head times the product of everything in the tail. And once we get to the empty list there, the result is 1. Now, as an exercise, you could easily see how to write a function which will compute the sum of all of the numbers in a list. It'll have a similar but slightly different definition. Now, what's cool is we can define yet a third or fourth, as the case may be, factorial function. Factorial triple prime of n is simply the product of the numbers from 1 to n. We're not going to do much with list comprehensions, but since they were mentioned in the brief overview description of Haskell, we at least include one example here. It's a kind of a set-like notation to define a list. So here we see a list in square brackets with an OR bar separating on the left-hand side the definition of the elements, and on the right-hand side the values that are used to inject into that expression in order to produce the list. So this list will give us the squares of x, where x come from the list from 1 to 10. So this is a very compact definition, and that results in the squares of the numbers from 1 to 10. Next, we're going to have a look at referential transparency. This is a very important feature of pure functional languages, and without this, lazy evaluation does not work. So a function has this property of referential transparency if its value depends only on the values of its parameters. That means that whenever we evaluate that function, it will always produce the same result. So for example, if I write the expression f of x plus f of x in Java or C++ or C or Python or what you will, it should be valid syntax in all of those languages, will that equal 2 times f of x? Well, in Haskell it should. In other languages it really depends, because f of x might actually modify x directly or indirectly. So the first time f of x is called might not give the same result as the second time it's called. In a language, a pure functional language, we have this property of referential transparency that guarantees that it doesn't matter when we call f of x or in what context, it will always give us the same result. As a consequence, equals can be replaced by equals. Now, let's have a look at how expressions are evaluated. Clearly, in the implementation of Haskell, it's a general purpose language, it's a practical language, it is implemented in a smart way. However, for us, for understanding what the semantics of Haskell are, we can imagine that it's evaluating expressions in a much more naive way. So let's take factorial of 4. Recall our initial definition of factorial being if n is equal to 0, then it will return 1, otherwise it's n times factorial of n minus 1. So what's factorial of 4? We can pretend that we simply replace the expression fac by its body. So if 4 equals 0, then 1, otherwise 4 times factorial 4 minus 1. Now, to evaluate this, we can't make any progress until we evaluate 4 equals 0. Well, 4 doesn't equal 0, so that's false. So in the next evaluation step, we reduce to 4 times factorial 4 minus 1. Now, we can't do a multiplication because we don't know what factorial 4 minus 1 is. We could evaluate 4 minus 1, but this is a pure functional language. We don't need that value immediately, so we apply non-strict evaluation, and instead we evaluate fac. So this expands, naively it macro expands fac to its body. So now we'll have 4 times, if 4 minus 1 equals 0, then 1, else 4 minus 1 times factorial of 4 minus 1 minus 1. Notice we still haven't evaluated 4 minus 1 anywhere. However, at this point, to make any progress, we need to compare 4 minus 1 to 0. So now we do have to evaluate it. So naively, we evaluate 4 minus 1 just once, so that becomes 3. So now we have to test if 3 is equal to 0. Now notice in this naive evaluation, we didn't compute the other instances of 4 minus 1. In a clever implementation, you would realize, 4 minus 1, they're all the same expression. If we evaluate it once, let's evaluate them all at the same time. We simply have a reference to the one location. So in fact, Haskell is smart enough to do that. But for all intents and purposes, it's equivalent to this. So let's pretend that they aren't evaluated. So now we have to evaluate if 3 equals 0. Well, that's false. So that gives us 4 times 4 minus 1 times factorial 4 minus 1 minus 1. And we continue and continue and continue until we finally get this monster expression. And now finally we're forced to evaluate all of these subtractions, and eventually we get the value 24. So this is the way you can think that Haskell is evaluating expressions, as lazily as possible. In fact, it's a little bit more clever, so that repeated expressions are evaluated only once instead of multiple times, which would be very inefficient. Now we'll see how this gives us how we can actually use lazy evaluation in practical settings. So lazy, or so-called normal order evaluation, only evaluates expressions when they're actually needed. When we have the lecture on lambda calculus, we'll see that we'll have a formalism that allows us to reason about different ways of evaluating the same expressions, either strictly or lazily, also known as normal order or applicative evaluation. So we'll see that in a couple of weeks. As I mentioned, clever implementation techniques avoid that replicated expressions are evaluated multiple times. Here we have a square function, so square of n is n times n. So square of 2 plus 5 would be 2 plus 5 times 2 plus 5, and when we evaluate that, in fact, the first 2 plus 5 being evaluated would cause the second one as well to be evaluated. So in a single step we could go to 7 times 7 and give us 49. Now, this is interesting. Lazy evaluation allows some functions to be evaluated even if they are passed incorrect or non-terminating arguments. So here's if true, which takes 3 arguments, a boolean, an x, and a y. And if the first argument is true, we'll get x back, and otherwise we'll get y back. So in other words, it's kind of if then else. Now we can pass if true the value true, and 1, and 5 divided by 0. In a strict language, 5 divided by 0 would have to be evaluated before we could evaluate the if true function. In a lazy language, we don't do that. So if true looks at true and x and says, oh, I should return x. It doesn't even look at y. It doesn't try to evaluate it because it doesn't need it. It just throws it away. So this is perfectly well defined in a lazy language. In a strict language, this would raise an error. Now, even more exciting is the notion of lazy lists. A lazy list is essentially an infinite data structure. If you try and evaluate the lazy list, of course your program will not terminate. But as long as you pass a lazy list into a program that only needs some of the values, you're good to go. So here's an interesting function, from. It takes an n, and it will produce an unending list, starting with n. The next element is n plus 1, and then n plus 2, and so on. So from 100, we'll produce the infinite list 100, 101, 102, and so on. So if we try to evaluate from 100, then our program would just not terminate. However, we can perfectly define such structures and pass them around as long as we don't try to evaluate all of the elements in the list. Now here's an application. I have another function called take, and it will take n elements from a list. So take is again defined by pattern matching. So we have 2 arguments and 3 different patterns. So if we take 0 elements from a list, that's going to give us the empty list. If we take any number of elements from an empty list, well, we'll only get the empty list back. So taking taking 10 elements from a list that only has 5 elements will just return those 5 elements. It won't be considered an error. Now the final case, take n plus 1 from a list with x at the head, will produce the list x followed by the n elements from the tail. So this is a complete definition. So now we can say, let's take 2 elements from the infinite list. So this would be evaluated as follows. First, we want to take 2 elements from the list 100 followed by from 101. This will pattern match our third case. So that will produce the list 100 followed by taking 1 from the list starting from 101. That forces us to evaluate another step of the from function, yielding the list starting with 101 followed by the lazy list from 102. We pattern match again the third case of the take function, and we pull out 101. And finally we take 0 from the lazy list starting from 102. But now we pattern match the first case of the take function, throw away the lazy list, and return the empty list, tack it on to the end, and now we simply have the list with 100 and 101 in it. So this shows us quite clearly that we can manipulate such infinite lists and use them in a practical fashion simply because they are evaluated lazily. Notice that the from function is built into Haskell with the special syntax list n double dot without any terminating value. So from 100 is same as left bracket 100 dot dot end bracket. So lots of sequences can be naturally implemented as lazy lists. Consider the following definition of the Fibonacci sequence. And here we're using a recursive function definition with a little helper function defined locally. So what are the Fibonacci numbers? They're 1, there's the list starting with 1, following 1, and then we want all the Fibonacci numbers that follow 1 and 1. Well, what's fibs following A and B? Well, it's going to start with A plus B, so the sum of the previous two digits in the list, and all of the Fibonacci's following B and A plus B. So there's a complete definition of a lazy list of Fibonacci numbers. And now we can simply pass that into our take function and take the first 10 Fibonacci's, and there we have them extracted. Now, a little bit more of an ambitious example, we're going to see how to define prime numbers as a lazy list. We're going to do this in a top-down way. So what are the prime numbers? The prime numbers, well, that's a list. It's a list of prime numbers starting from the prime number 2. Well, what are the primes starting from number n? Well, it's going to be a list starting with p, where p is a prime number, and followed by the primes from p plus 1. So p should be the next prime following n. Okay, we need the next prime function. What's the next prime function? Next prime n, what's that? That's going to be the next prime following n. So if n is prime, then we're done. Otherwise, we're going to look for the next prime starting from n plus 1. So now we need the is prime function. Well, we can solve that by pattern matching. 2 is prime. And n is prime if n is not divisible by any of the primes in the set called primes here. Where primes is the infinite list of all prime numbers. However, we can be intelligent. We'll use Eratosthenes' sieve. So not divisible will take some list of primes starting with k. And if k squared is bigger than n, so we've checked all the primes up to k, and it's not divisible by any of those, and if k squared is bigger than n, then we can stop. Then we know that n is a prime number, because it's not divisible by any prime number up into its square root. If, on the other hand, n can be divided by k, well, then n is not a prime number, so we return false. And the last case, it's not divisible by any prime up into k. K is still smaller than the square root of n, so then we'll have to continue searching. So we throw away k and continue looking at the tail of the list, the p's, the primes in the tail list, and recursively continue searching. Eventually we'll stop because we'll eventually reach a prime number that's when squared is bigger than n. Now we've defined all the parts, and we have a complete definition in a very declarative style of a prime number algorithm, purely defined in a functional way, without any side effects. And the result is a lazy list. So now we can take the first 100 primes, and that works quite efficiently. Now, let's take a closer look at recursion in pure functional languages. So in principle, recursive functions can be less efficient than loops because the cost of procedure calls is fairly high, because you have to create an activation record for every function call and maintain a runtime stack of function calls in order to evaluate these functions. So you're pushing and popping on the runtime stack, and that's more expensive than a simple loop. However, if you have a so-called tail recursive function that only calls itself as the last operation, then the recursive call can be optimized away, since you only need a single stack frame on the runtime stack. So when we compute factorial 5 needs a stack frame on the runtime stack. It calls factorial 4, that needs a stack frame, which calls factorial 3, and so on. But if we rewrite factorial to be tail recursive, then sfac of 5 will, as a last step, call sfac of 4, and so on. So we can reuse the current stack frame, and we don't have to do any pushing or popping on the runtime stack. So what would that look like? We can take a recursive function and convert it to a tail recursive one by representing partial computations as an explicit function parameter. So basically we're accumulating the result without any side effects and passing it as an additional parameter. So factorial is a case where what we want to do is we want to accumulate the multiplication of the numbers n times n minus 1 times n minus 2 and so on. And since we don't have a variable that we can update, what we can do instead is compute that partial result and pass it in as an argument to the recursive call. So sfac of Sn, the n is what we want to compute the factorial of, and S is where we're going to accumulate the product. So in the recursive call, if n is 0, that means that we're at the end of the computation and we simply return S. Otherwise, we'll take n, multiply it by S, and pass it into the recursive call. So we're accumulating our product, and in the second argument, we're reducing n. Again, we're not having any side effects because we're not updating any variables, but we're simulating that by passing the updated values to the recursive call. So now to compute the factorial of 4, we'll call sfac of 1 and 4, initializing this product. So sfac of 1 and 4, by the recursive calls, we can see that eventually we're going to return 1. So the initial value of the product times 4 times 3 times 2 times 1, which evaluates to 24. And this is completely tail recursive because the last thing that we do is call sfac. So notice we either return S or we return sfac of S times n minus 1. So the last thing that's done is the recursive call. That's the tail recursive function. Multiple recursion can be dangerous. So if you have a naive recursion with multiple recursive calls, that may result in exponential complexity. So here's a naive Fibonacci function. So Fibonacci of 1 and 2 are each 1. Fibonacci of n plus 2 is Fibonacci of n plus Fibonacci of n plus 1. Notice this is not tail recursive. Why? Well, take a close look. What's the last thing that happens here? It's not calling Fibonacci, it's calling the plus of the 2 Fibonacci calls. So it's not tail recursive. Worse, each of the calls to Fibonacci is going to be recursive, so you're building up an exponential tree. Now we can do the same trick that we had before. We can regain the efficiency by explicitly passing the calculated values. So here, Fibonacci prime, Fibonacci 1 is 1, Fibonacci of n is a, where a is the second element of the pair of numbers in fib pair of n. So fib pair is a little bit cleverer. It computes always a pair of Fibonacci numbers. Remember, we did the same thing in our PostScript implementation of Fibonacci's, where we were always computing a pair of Fibonacci numbers and jumping up to the next pair, and that computation is linear. So the first Fibonacci pair of 0, 1, and the nth pair is b, a plus b, where a and b is the n minus 1 Fibonacci pair. A little exercise for you would be to write a tail recursive Fibonacci function. Now we finally get to the last topic in today's lecture, and that's the story of higher order and curried functions. Now, a key property of pure functional languages is that functions themselves are first-class values. What does the term first class mean? First class means that a value is first class if it can be treated like any other value in the language. So in an object-oriented language, for example, objects are first class. We can create them and pass them around. But there are certain things which are not first-class entities. For example, a class is not a first-class thing. I cannot create a class at runtime, not normally. In some languages I can. In Smalltalk I can do it, but not in Java. A method is not really a first-class thing. With the help of reflection, and I can get a handle on a method and a representation of a method and do something with it, but it's not a value like other values. There are other things which are also not first-class values in languages like Java. For example, an if-then-else is not a first-class thing. A package is not a first-class entity. I can't have a method that takes as an argument a package. It's simply not part of the language. So what we strive for in the design of languages is to be as general as possible so that any kind of entity can be a first-class thing. Well, in pure functional languages, functions themselves are first-class values that can be passed around. Now, what can we do with that? Here's an example, a very well-known example of a map function. Map takes a function and a list and returns a new list where every element of the original list has that function applied to it. So if we want to map f to the empty list, that gives us the empty list. And if we want to apply map f to a list with x at the head, we simply return the list with f of x at the head and map f to the tail. That's a complete definition of the map function. So if we map the factorial function to the numbers from 1 to 5, then we get the list of the first 5 factorials. Now, what's interesting about that is mapFac is a new function that can be applied to lists. And this looks kind of strange. So mfac of L is map of fac to L. So now mfac is a new function which maps factorial to a list. So mfac applied to the list from 1 to 3 is the list of the first 3 factorials. In addition to functions that are defined using the mechanisms we've seen so far, pattern matching and so on, you can also have anonymous functions that are unnamed. This concept has also made its way to many other programming languages. Most recently, Java has had anonymous functions added to it. The syntax of anonymous functions, as we'll see, is inspired by the lambda calculus. And to simulate the syntax of a lambda, the Greek letter lambda, we use a backslash. So here's an anonymous function, backslash x, arrow x times x. That's the anonymous function that takes an argument x and returns x times x. So here if we define square x equals x times x, we can say square of 10, but we can equivalently write the anonymous function inline and apply it to the number 10, and that gives us the same result. Anywhere we expect a function, we can also pass in an anonymous function. So here, for example, we can map the anonymous square function to the numbers from 1 to 10 and get the first 10 squares. Now, curried functions. All the functions we've seen up until now are actually curried functions. This has nothing to do with the food. This is named after the logician H.B. Curry, who studied such functions. A curried function takes its arguments one at a time, so it's actually treated as a higher order function. What does this mean? So here's an example. Plus of x and y computes the sum of x and y. But what's special about that? Plus of x and y is actually a curried addition. So it takes its argument x first and returns a function, an anonymous function, which will take a y and return x plus y. We'll see that in a moment. The normal addition would take a pair of numbers, written with the syntax with round brackets and commas. So plus prime of xy also returns x plus y. It's a different function. It's perfectly normal addition. Plus prime takes a single argument. Plus takes two arguments, but takes them one at a time. Let's see if we can make this clear. When I write something like plus xy equals x plus y, that's actually just syntactic sugar for plus x equals lambda y arrow x plus y. Let me say that again. A curried function that takes multiple arguments is simply a function in its first argument returning an anonymous function that takes the next argument. So plus 5, 6 is actually plus 5, which returns an anonymous function that adds 5 to its argument, applied to 6. In other words, we're invoking plus 5, obtaining a function lambda y returns 5 plus y, and we pass the argument 6, and we finally get 11. So what's cool is, until I told you this, you never noticed that we were working with curried functions all throughout the slides up until this point, because it didn't matter. So for most purposes, we don't care when we're using curried functions, because they look just like ordinary functions, but when we need them, they're very, very powerful. As a consequence, we can write something like this. Inc is equal to plus 1. Plus 1 returns the anonymous function that adds 1 to its argument. Except now that we've bound it to the function named inc, so now it's no longer anonymous. So inc of 2 will give us 3. Now, sfac, recall, sfac took 2 arguments, but sfac was defined as a curried function. So now we can simply say fac is equal to sfac of 1. And we can define it locally using a where clause. So fac is equal to sfac of 1, where sfac of Sn is blah, blah, blah. Now, suppose we've got a function that's not defined as a curried function, and we want to turn it into one. Well, here we've got it. Curry of f a and b is equal to f of a and b. So f was originally defined as a function taking a pair, a and b, and now we've curried it. So suppose we have, as an example, a plus function that's not curried, that takes the pair x and y and returns x plus y. And now we can apply curry to it to make it a curried function. And now we can define inc as curried version of plus with the first argument passed in, which is 1. So this may seem a little bit like magic, but I encourage you to take a close look at what's going on in these slides here, because it's important to understand what we're doing. Similarly, if we have an sfac version that takes a pair of arguments s and n, defined in the obvious way, then we can take our magical curry function to curry it and bind the first argument. Well, there's still a lot more to see, and we'll continue next week. We'll have a closer look at some of the further features that we need from Haskell, in particular enumerations. We'll see how to define user data types, and we'll see how type inference works in Haskell. So Haskell is a statically typed language. Every program that we've written before was interpreted was type checked, but you may have noticed that never once did we declare the type of any of our functions or parameters to functions. So something is going on that we didn't see. So what Haskell does is it actually looks at any of the programs that we write, and it tries to infer what the types are if they're missing. Of course, we can write explicit type declarations, and next week we'll see how to do that. But what's amazing about languages like Haskell is that with the help of type inference, for most programs we don't need to write the types, but the language will ensure that our programs are type correct. We'll also see that Haskell supports something called type classes, which are very different from object-oriented classes, but are important for us to be able to write generic code. So that's for next week. Thanks very much for your attention.